Hello, and thanks for joining again. This is Greg Moore from TAFE New South Wales. We're doing a small lesson on the voltage divider, which was mainly prepared for the homework for DC circuits in week 5 for UEENEEE104A. Getting right into it then, look, what I will do, I will just introduce the fact that, as most know, it's available on this website, and here it is here, DC voltage divider theory. And they're the pages for the theory. Despite the fact that some of it was written in pages and some of it wasn't, because I am an Apple person. Anyway, look, to make it easier for this video, what I'm doing, I'm using the actual Notability app that I do most of my writing in to go through, just in case there is something there that I do need to annotate. So here we go, 2018 March, and I've got here, watch the video. Well, guess what? This is the video that we're currently making. Simple voltage divider, we've done this in class. Battery, source of voltage, 2 resistors, identical size resistors, V out, half the battery voltage. That is providing we don't get any meter loading. If we've got a low resistance meter, that meter then will be in parallel or shunt with R2, make a new lower value resistance there, and we would get less out. So if you're using a DMM, which has got like 10 million ohms of resistance, you're not going to get any meter loading, you're going to see 5 volts. And the equation for that is V out equals Vs times R2 divided by R1 plus R2. And here's R1 on the top, there's R2, so you get the sum of the 2 of those. And we'll look at this. There's going to be a lot more in this series of resistances. In this very simple pattern here, there's only 2. But we always, when we use this equation, break it down into just 2. We lump like things together. And I've got some other notes on that as well. All right, so that's an easy calculation. In this circuit, RL loads down. So what I've done here, I've added RL now, because a voltage divider, let's face it, it has to power some other part of the system or part of the circuit. So, building the voltage divider and saying, hey, I've got 5 volt supply here, I can run a little motor that works on 5 volts. No, it's not going to be that easy, because the motor draws too much current, and that current's going to cause a big voltage drop across that resistor, and you're going to get a lot less than 5 volts out. So this type of voltage divider, although we call it a simple power supply setup, it's a very primitive power supply that can only power a little bit of current. And that is depending on the value of these resistors, because we've got what's called a bleed current that comes down here. And if that bleed current running through R1 and R2 is much bigger than RL, well, the system works. The output voltage will be reduced a little here if RL is big enough in comparison to the 1K, that is. So I've said here it'll be reduced a little because the new R2 value is R2 in parallel with RL. So RL has to be much smaller than R2 for this to work effectively. I've said again, be careful of meter loading. The meter may have low resistance and load the circuit. So I've got this beautiful purple texture color that comes up here onto that top circuit. Meter loading is always something we need to be aware of in the electronic industry, especially in current meters, moving coil current meters. We've seen this in labs as well, where the resistor might have as many as 20 or 30 ohms of internal resistance when it's reading low milliamp values. And in small circuits, that can really cause mayhem with the calculations, especially if you've used a circuit simulator to do the calculations for you in the first place, and the circuit simulator had a current meter resistance of about 1 micro ohm, which, as we saw in real practice, that's never going to happen. So look, I've put an orange box here showing that RL must be large. The load resistor must be large in comparison to R2. Why? So as not to cause too much loading on the circuit. So here again, I've got 2 resistors, the same value. The output is going to be 1/2. And in fact, if we look at the REQ for this, we've got 500 ohms. If that was R2 and that was the load of the same value, I'd be making R2 now instead of 1K to take it down to 500 ohms. So that's very impractical. That's going to throw the calculations right out the window. But where we've got a much bigger value, like more than 10 times the size we're going to see later, 1K, 27K, I've done the sum of the conductances here to get the, and then taken the reciprocal of that to get the overall resistance, and I get 964 ohms, which is a very, very minor change, and it won't load the voltage divider down very much at all. So large resistor, which is drawing the current from the power supply, and a big bleed current, which means a smaller, much smaller resistance there. And we're going to see that this should be about 10 times the value of this. And I'll say this again later on. I think there are some websites that got this around wrong. And I've looked at a couple of websites and people got this the wrong way entirely, which is just not right. So we see that RL must be much, much greater in resistance in comparison to R2, R1 combination. Sometimes the bleed current, if we do have to draw a little bit of current out of this, I need a lot of current going down through the bleed resistors. And in this case, we can have 80.6 milliamps if we have 10 volts with 91 ohms and 33 ohms. So the bleed resistors are going to come very hot, and they're going to waste a lot of energy to give us this 2.66 volts out. But we do say that that is quite a stiff voltage divider, and we can put quite a variation in loads on that, and we won't change that 2.66 volts very much within a certain current range. So I've said here, although we're going to waste a lot of energy, we can draw a lot of current from the V-out terminal. All right, so if we run the power calculations on that, look at this. I got PR1 590 milliwatts, 0.64 watts, and PR2 214 milliwatts. So that's nearly a watt of wasted energy there. The 10 times rule, I've already mentioned that a couple of times. If the value of RL is 10 times bigger than the bleed resistance, the output voltage will not change very much. And that is the secret with these things. Look at this, 33 ohm resistor as R2, 330 times resistor. It's 10 times bigger. I looked at the maths on this, unloaded. So unloaded, I take that away completely, and I've got 33, which is R2 on the sum of the two times the 20 volt rail. 5.32 volts is the unloaded output voltage. The loaded voltage, R2 is going to be the combination of 33 in parallel with 330. Look, parallel combination there. And that makes it 30 ohms. So 30 over 121, which is the sum of the two, and times 20 volts, 4.96 volts. And that's going to... and 4.96 volts is not dramatically different. It's a 6.7% reduction, which it's less than 10%, so that's quite acceptable. So we see that a stiff divider is good, but wasted power in the heat is bad. All right, so if we put a lower value resistor there, just to look at the alternative, 33 ohms, 91 ohms, 82 ohms, ooh, it's not much bigger than this. Run the maths on that, we get an REQ of 23.5 ohms, V out 4.1 volts DC, the error is going to be 1.25 volts. There's our unloaded. There's our new voltage, and we run the percentage on that. We've got 23% error now. So you can see as you start drawing current out of this voltage divider type supply, it's really not a good thing at all. What if the divider stiffness was poor? What if we really exaggerate this a lot and we go to 910 ohms, 330 ohms, 82 ohms? Wow, now I've got a huge resistance here and a little resistance here. Let's look at the maths. Run the maths on it using the new REQ, and I get a V out of just 1 volt at this point here. So that's going to be absolutely useless to us compared to the 5.2 volts that we had in the unloaded situation. Now let's go on and look at the load current, bleeder current. In this new circuit, I've got 3 resistors in the voltage divider, and I've got 2 output voltages. I've got VA and I've got VB, and each one is connected to a different value of load resistor. This one is 18K, this one is 10K. And they're quite large values in comparison to these, because look, that's just 560 ohms, 330 ohms down here, and 220 ohms in the middle. So these are much more than 10 times the value of their equivalent resistors over here in the, or their side resistors over here in the voltage divider. I've written the load value resistors down here. Find VA, find VB, find all the currents. Very typical question to be asked in a test, and it's something that all electronics guys should be able to do. Here's the solution. I've put a circle around the bottom part of the circuit, and I've said RL2 in parallel with VB, got a new REQ, 319 ohms. Redraw the circuit now. I've got the 319, which is in this red loop, and then that's in series with the 220, which is here, and then the whole lot has 18 k ohms across it, and you can see that there. So I've done the maths on that. I've added and I've multiplied product over sum to get 523 ohms. And that 523 ohms is going to be from this VA point down to ground. So I've re-sketched the 2 new equivalent resistances, 560, 523, to get 1083 ohms. And I've run the maths on that to get the current total flowing down through the voltage divider, which, by the way, includes the load currents as well. Because don't forget, I've got a quiescent current, we call that, just a standing current going down through the voltage divider. But now I've got, it's the bleed current, and now I've got this other current flowing into load 1 and another current flowing into load 2. So I've redrawn it down here. We're going to work out that total current, and 24 volts supply divided by 1083 ohms, 22 milliamps. And I rounded that down. But look what I've put in brackets here, 22.16066. And I know any other day I'd be complaining, saying you've got obsessive compulsive disorder if you go that many decimal places. And people would be saying the same thing to me when I'm at the front of the classroom. Why have you put so many decimal places? Well, we're going to find out shortly that we probably need those, because the first time I rounded this down by that 0.2 of a milliamp, which I didn't think it'd make a lot of difference, I found out later it sort of did make a lot of difference, and it didn't work out too well. So I've put a little dash underneath this 22 milliamps where I multiplied it by the 319 ohms, which was that REQ we got up here from VB down to ground. And it told me that VB from VB to ground was 7.07 volts, and that's on this meter here. And VA is going to be 22 milliamps times 532 ohms, which that was 532 ohms REQ from VA down to ground. That was all that calculation that we did there. 11.6 volts DC. But what's going on here? If you're new at this and you haven't done it before, you add that voltage together and you add that voltage together and you go, hang on, these don't add up to 24 volts. What's going on here? And you scratch your head a little bit. So I've gone over on the next page and I've done the solution a slightly different way. I've used the colour loops that we've used many times before with parallel and series resistor networks. And I start as far away from the battery as I can. I did this orange loop around here, 10K, 330. Remember that? 319 ohms. We saw that before. And then that was in series with 220. So that becomes that purple loop. Look, 539 ohms. That's everything inside that purple circle there. And then the next loop was the green loop. And everything in there is 523 ohms. Do you remember that? We had 319 and 523. Here they are here. We had 319, 523. No different, just a little bit, in my way of thinking, a little bit neater way of doing this. So I've run a current divider on this. And the current divider, as you know, is I18K, the current in the 18K resistor, will be Req over 18K times the input current to that node. And I, 539 ohms, Req over 539 times 22. And I went ahead and I worked that out, 639 microamps and 21.3 milliamps. Have a little note of this though. Look, 22 milliamps, circle around it, 22 milliamps, circle around it, sort of a line drawn cautiously under here saying, you know, something's definitely gone wrong in this maths. When I first did this simulated circuit and I looked at the right values and I went, hang on, I seem to be out by a little tiny bit that I cannot account for. So I went back into that 22 milliamps and that look at before, and I think it was up here somewhere. There it is, 22.16066 milliamps with a little bit of OCD added in there to get that big value. All those decimal places, but that value is going to become very, very important to us because I went ahead and I did things with the rounded down value to get 639 microamps, 21.3 milliamps, and then I went into current divider 2 and that threw those calculations out as well. So I originally ended up, after doing my 2 current dividers, because I've got this one at the end and then I've got this other one here. Do you see the red line here on the circuit? I've got 639 microamps, 21.3 milliamps. These calculations, no, that's not quite as good as it should be because I got originally 11.5 volts and 6.86 volts. No, 6.8 volts. And when I came down here, I looked at the maths here in the simulator and I see I've got 11.6 volts and 6.87 volts. I'm out by too much, 6.87. Look, I'm out by a significant amount there and I'm out by a significant amount there. And that was when I went back in and I got these new values by using the full value of the current, which was the 22.16066. 2.16066. Yeah, that's looking good. Okay, I'm happy with that. I don't know why I didn't write that on that page before. So it just goes to show now, rounding can cause a lot of problems when we've got very small currents and very small voltages involved. So don't fall for that trap. It caught me, and I caught up with it because when I went to the simulator and I looked at the right values, and anyway, the maths did not stack up. When you do your maths, again, going back to what I said before, these values don't add up. 11.6 volts, 6.87 volts, they don't add up to 24 volts. Why not? What's going on here? Well, you know, look, let's do that and then I'll come back to what's in blue. The addition, I need to go 24 volts, which we start with, minus 11.5599. That gives me a difference of 12.401 volts across 560 ohm. And then I've got the 11.6 minus the 6.87 to give me 4.73 volts across that, you see? And then I had that 6.87, say, down here to ground. And if I add each of these together, that plus that, bingo, we've got what electronics is all about. It's the maths. The maths always has to add up, and there's our 24 volts. So originally when I was like out here, what did I have? I had 11.5. I was out by 100 millivolts, should be 11.6. I had 6.8. I was out by, 60 millivolts. So that was enough to throw my answer, just enough, and make me think I've made a rounding error in this circuit. I mean, I wasn't dramatically wrong, but I was wrong enough that things were not good. Now, in the blue, Final proof shows the importance of the decimal places and the rounding error. Always use the full current. Now I'm going to go back up to here where we had that, like, wow, why don't things add up? And look at this, 7.07 volts DC. That's nothing like that 6.6 volts. That's way above it. What the heck have I done here? Well, I worked on the 22 milliamps and I said the 22 milliamps keeps flowing down through the loop. No, it doesn't, because we've lost some of the current here through the first RL1. And then we had less current coming into that second network. So look, 22 rounded milliamps comes into the whole network, but then only 21.3 milliamps comes into the second network. So I didn't see that, and you wouldn't have seen that if you do it this way that I've done it up here without using the looping. It's an easy trap to fall for. So I always like to break the circuit down and put loops around, start from the far side, come right across, and look at my Kirchhoff's currents when I do this, knowing that I've got current forking taking place here. I've got the current entering the network, has to be the same as the current effectively leaving the network. The maths has to add up to. And the fact is that I've got this input current minus this current to leave this current and satisfy the maths. So 21.3 milliamps coming into there. That's why that 7.07 was just way out compared to what we really wanted. So make sure you run the simulation. If you haven't spent the $15 yet, please buy something like iCircuit. There's a couple of different things you can buy. I recommend this one. I think it's nice and cheap. Runs on the PC, runs on Android, runs on the Mac, probably even runs on your iPhone, I'm not sure. And then we've looked at the additions there. That all added up. And then finally I've said, look, it can also be solved using extensions of R2 over R1, R2. That's kind of what I did in the first place, but you can really make this look complicated and way overcomplicated. And if you have a look at the Floyd book, 8th edition, page 245, that's what Floyd did. And it's not a bad thing to do either. Also, you can Thevenize the circuit. And if you look at what the Afro Tech Mods video, and you see that we get the power supply or the battery and we say, well, it's effectively got no resistance, so we can put a short circuit where that is. And then that R1 and R2, they work as if they're in parallel, feeding the network where the current's being drawn from. So this is something that you do if you do circuit analysis subject down the track. So that's just going a little tiny bit beyond with Thevenization, what we do in UEENEEE104A. We don't do too much of that. So I've just sort of mentioned it briefly. He's used it in the video. I hope you can see the purpose of that. And that really helps us to solve a lot of complexities in circuits down the track. So if you're doing the diploma or the advanced diploma course, you'll be using Thevenin's and Kirchhoff's and nodal analysis and mesh analysis and all those sorts of things. But for the basic DC circuits, we do not do that. All right, hope that helps. This has been Greg Moore for TAFE New South Wales with the voltage divider tutorial, which was specifically done to help with the homework assignment in week 5 of DC circuits. Okay, see you next time.